Well, I've been waiting for this one. A voltaic cell similar to that shown in figure 20.5 is constructed. One electrode half cell consists of a silver strip placed in a solution of silver nitrate. The other has an iron strip placed in a solution of iron 2 chloride. The overall cell reaction is given. A. What is being oxidized? What is being reduced? Okay. You take electrons off a silver plus, you make a strong oxidizing agent. So silver plus is taking the electrons away from the iron. The iron is being oxidized. The silver plus is being reduced. That means that iron is at the anode. All right, that's where oxidation occurs, anox. And reduction is occurring at the cathode, red cat. Okay, so write the half reactions that occur at the two half cells. Well, here they are, right? So we've got iron losing 2 moles of electrons and 2 moles of silver, ion gaining 2 moles of electrons. C, which electrode is the anode, which is the cathode? Did that. So D, indicate the sign on the electrodes. All right. So at the anode, you're losing electrons. They're traveling through the wire, through the voltmeter, over to the silver plus ions on the other side. So the electrons emanate from the iron. All right, this makes it the negative terminal. All right, so this is where the electrons come from, and they go over to the positive terminal. All right, so negative sign at the anode, positive sign at the cathode. E, do the electrons flow from the silver electrode to the iron electrode or from the iron to the silver? In which direction do the cations and anions migrate through the solution? Okay. So I did a rendition of this cell. All right, so we've got iron at the anode losing electrons. We've got silver plus at the other side gaining the electrons. The anions are just there to balance the charge. All right, so as iron loses electrons, all right, they travel through the wire, put work through the voltmeter, and go over to the cathode, where the silver plus ions grab them. All right, so as the iron loses electrons, you're wearing down your iron strip. It's turning into iron 2 plus. So as this reaction goes forward, I'm building up a plus charge over at the anode. Over at the cathode, as the silver pluses take the electrons, I'm lowering the concentration of silver plus, raising the concentration of iron 2 plus, so I'm building up a negative charge over at the cathode. So this is where the salt bridge comes in, right? The cations, the non-reactive cations and anions in the salt bridge are just there to run to the side where you're building up a negative charge and a positive charge. So as I build up a positive charge over at the anode, the chloride ions run to this side to neutralize that buildup of charge. Over on the cathode side, where I'm building up a negative charge, the cations, right, the potassium ions run over to this side to cancel that buildup of negative charge. And in this way, the electrons will keep flowing. All right, so as long as we don't build up a charge, the electrons will keep flowing from the anode over to the cathode. What does the term electromotive force mean? All right, electromotive force is how much push the electrons have going through the wire. This is measured in volts. So that's what volts are. How much push do you put on those electrons? What is the definition of volt? Okay, so again, right, joules per coulomb. How much energy you putting into the electrons? All right, so joules over coulomb is the unit for volts. So if I know how many coulombs are going through, multiply coulombs by joules per coulomb, and I can get the energy being generated by these electrons going through the wire. All right, the voltage of the cell, that's the cell potential, right? So what kind of voltage is the cell generating? And that's going to be determined by what the concentration of the reactants in the products are. A voltaic cell that uses the reaction thallium 3 plus reacting with chromium 2 plus to make thallium plus and chromium 3 plus. has a measured standard cell potential of 1.19 volts. A, write the two half-cell reactions. All right, so this is thallium 3 plus taking 2 moles of electrons to become thallium plus, and chromium 2 plus is losing a mole of electrons to become chromium 3 plus. All right, you'd have to multiply the half reaction of chromium 2 plus turning to 3 plus by 2 in order to get 2 moles of electrons coming out of the reaction for every 2 moles of electrons going in. And B, by using the data in Appendix E, determine the reduction potential for thallium 3 plus going to thallium plus. All right, so we know what the cell potential is, right? The cell potential is equal to the oxidation potential plus the reduction potential. So what I need to do is look up on the data chart what the reduction potential for chromium 3 plus is, turn it around, turning it into the oxidation potential for chromium 2 plus, and changing the sign. Now I know what the oxidation potential is for chromium, and I know what the cell potential is. I can just subtract the oxidation potential from the cell potential to get the reduction potential for thallium 3 plus. All right, C, sketch a voltaic cell, label the anode and the cathode, and indicate the direction of the flow of electrons. All right, so let's clean this up. I want to get rid of the anions that balance the charge and just look at the reactants turning into products. All right, so notice we had no solids here, right? This is a ion in solution losing electrons to another ion in solution. So we have to have a surface that this occurs on. So it's happening along a platinum surface. Platinum is a good inert metal. It's not going to react. It holds onto its electrons strongly. So as chromium 2 loses its electrons and thallium 3 takes the electrons flow from the anode over where chromium 2 plus is losing electrons over to the cathode where thallium 3 plus is gaining them. So as the electrons flow, the concentration of the chromium 3 plus builds up, and the concentration of the thallium 1 plus builds up, and I generate a voltage. Right, so at standard conditions, I'd have a 1 molar concentration of the chromium 3 plus and a 1 molar concentration of the thallium, a 1 molar concentration of the chromium 2 plus and a 1 molar concentration of the thallium 3 plus, and this would be the voltage that would be generated, 1.19 volts. Again, 1 molar concentration of the reactants. Using standard reduction potentials, Appendix E, calculate the standard EMF for each of the following reactions. Well, we look up on the reduction potential table what the reduction potential is for chlorine, and we look up the reduction potential for iodine, switch iodine around and turn it into an oxidation potential, change the sign and add them together to get the voltage. So it's the same with the rest, right? Nickel is the thing being oxidized in B. So turn its reduction potential around, turn it into an oxidation potential. That means changing its sign, add it to the reduction potential for Ce4 plus turning to Ce3 plus, and get the voltage. Iron 3 plus is taking electrons. Iron solid is losing electrons, turning to iron 2 plus. So this is where iron 3 is taking electrons, turning to iron 2, and iron is giving up electrons to form iron 2. So when you add these together, you get, you get iron reacting with iron 3 to make 2 iron 2 pluses. Look up the reduction potential for nitrate, and look up the oxidation potential for copper 2 plus, turn it around, turning it into an oxidation potential, add them together to get the voltage for the cell. So this is how we use the reduction potential chart. For From each of the following pairs of substances, use the Appendix E to choose which one is the stronger oxidizing agent. So when we look at the reduction potential chart, we see that chlorine is the stronger oxidizing agent, right? It has a larger reduction potential. That cadmium 2 plus is a stronger oxidizing agent than zinc 2 plus. Chlorate is a stronger oxidizing agent than chloride, and that ozone is a stronger oxidizing agent than peroxide. By using the data in Appendix E, determine whether each of the following substances is likely to serve as an oxidant, an oxidizing agent, or a reductant, a reducing agent. All right, so a reduction potential table. All right, we've talked about it before. We've seen it before. It's laid out according to how strong an oxidizing agent you are, right? So at the very top of the chart is fluorine. This is the best taker of electrons, right? So it has a very high positive reduction potential. And as I go down the list, become less and less of an oxidizing agent, weaker and weaker. There's a delineation point, right? If I could take one side of the chart and put it under the other, we keep going down until we'd hit hydrogen. H plus ions taking electrons to form hydrogen gas, which has a 0 voltage. Anything below it has a negative value. All right, so you're decreasing strength and oxidizing agent as you go down the list, right? A reduction potential chart. So looking at chlorine, it's fairly high on the chart, right? So this is a good oxidizing agent. Even better is permanganate. Permanganate's even higher in the chart, right? It has a more positive reduction potential. So this means that if I reacted chloride with permanganate, right? Chloride's on the other side. This is what chlorine forms when it takes 2 electrons. So put electrons onto an oxidizing agent, you make a reducing agent, right? It sounds like acid-base chemistry, right? Put an H plus onto a conjugate base and you make a conjugate acid. All right, so this chloride has the potential for giving up electrons now. And yes, because permanganate's a stronger oxidizing agent than chlorine, it will take electrons off of the chloride to make chlorine gas. So this is one of the ways we generated chlorine gas earlier in the year. So the lower you are on the chart, the less of an oxidizing agent you are, and the more the product of what you're making is a reducing agent. So put 2 electrons onto barium 2 plus. Barium 2 plus is a miserable oxidizing agent, but barium metal is a really good reducing agent. So if I flip this around, turn into barium 2 plus, by removing 2 electrons, I would change the sign on the reduction potential of negative 2.9, making it positive 2.9, and make it an oxidation potential. I could add it to a reduction potential to get the voltage at standard conditions, 1 molar concentrations for the cell. So same with zinc. Zinc metal is a better reducing agent than zinc 2 plus is an oxidizing agent. Given the following reduction potential half reactions, right, so they're giving us voltages here in these half reactions, write the balanced chemical equations for the oxidation of iron 2 plus by I don't know what that is, S2O6 2 minus, I don't know, an anion that obviously is a strong oxidizing agent, right? So if I put this together, right, iron 2 plus losing electrons turning into iron 3 plus, I turn the reduction potential for iron 3 plus around, make it an oxidation potential. I add that to the reduction potential for S2O6 2 minus, and add the two together and get the voltage for the cell. All right, so multiply it by 2, so you get 2 moles of electrons going in and coming out. And notice that has no effect on the voltage, right? So balancing these half reactions, that when you add them together to get the overall reaction, has no effect on the voltage of the cell. So I cancel the electrons and I end up with the balanced redox equation. Or I should say the net ionic equation, right? I'm emitting spectator ions here for the voltage at standard conditions. All right, so hey, a negative voltage. This tells me this is a non-spontaneous reaction. Actually, iron 3 plus is a better oxidizing agent than S2O6 2 minus. If I'm doing B, oh no, I'm sorry. B, they wanted us to calculate the delta G naught value. So the negative value for the voltage, this implies a non-spontaneous process, which implies a positive delta G value. So if you look at the relationship between G naught and E naught, N stands for moles of electrons being transferred, F is Faraday's constant, and if you multiply negative NF by the voltage, it's a way to convert to free energy change at standard conditions. So 2 moles of electrons were transferred, multiplied by Faraday's constant, moles of electrons cancel, multiplied by volts, which is joules per coulomb, coulombs cancel, and I'm left with joules. C, calculate the equilibrium constant for the reaction. All right, so just like G naught it can be set equal to the equilibrium constant, so can E naught. All right, this is called the Nernst equation, or a permutation of the Nernst equation, where if I know what the voltage is at standard conditions, I can equate it to the equilibrium constant. So N stands for moles of electrons, 0.0592 as a constant, which included Faraday's constant to derive it. So divide moles of electrons into this constant multiplied by the log of K, and that would be a way of equating K to the voltage. But I know the voltage here, so multiply both sides by 2, divide both sides by 0.0592, and take both sides to the base 10. And this would be a way of getting the K value. So again, negative voltage at standard conditions implies a non-spontaneous reaction, a small K value.